Kwaśniewski. And the title of his talk, as you can see there, is From Twisted Inverse Semigroup to Twisted Self-Similar Actions under Sister Algebras. Please, Bartosz, go ahead.
Thank you. Thanks for having me here again. Apparently, last time I didn't misbehave that badly, so you invited me once again. Okay, so today I will speak about my joint paper with Alex Monday, who visited Białystok roughly 2.5 years ago for almost a month. So we started discussing things, and this is me. So we started discussing things, and Alex said that he likes this. He was working on this self-similar stuff, and I was interested in this twisted non-Hausdorff things. So we decided to combine this, and this is kind of the result. I mean, the result is now 90 pages long dissertation. And so the main novel things that we included in our approach is that we consider self-similar actions with twists, and we would like to consider general actions, not necessarily faithful ones, and actions on general graphs. Some people claim that they work with general graphs, but I agree to disagree. So twists were kind of introduced by our host here. So really consider twists, but in a slightly different setup. I will come back to that. Also, this was algebraic and studied different problems. So our twists these are kind of different. There is a small intersection, but very small. And we also added, we not only consider algebras, but with Toeplitz extensions. We also consider subalgebras, this core subalgebras, too many things. And on top of that, this is my fault. We also included everything in this LP context. So I will mainly focus here on the sister algebraic, but most of things generalize to this LP operator algebra context. Okay, so let me start with this paraphrasation of this diagram from a Excel paper on inverse semigroups and combinatorial sister algebras. So he claimed that when I start with combinatorial data, one should associate with an inverse semigroup and an ample groupoid and operator algebra. I would claim that it is good to know all the arrows, not necessarily only those. And in this talk, this is kind of approach, usual approach. Our discrete data will be this self-similar groupoid action on a directed graph. But since we wanted to add a twist, so in fact, our data will be twisted data. And for this, we need to rewrite the whole diagram. So we need to add two twists everywhere. And apparently, this theory does not exist in the literature, this twisted case, general picture like this. So therefore, half of my talk, I will kind of try to present general approach to this part of the diagram. And then I will go back to this self-similar groupoid action. So this is what we did with Alex, and in particular with this particular twisted data here, if it is this twisted self-similar groupoid action, we can also add to this diagram the sister correspondence analysis. Okay. So let me start with a brief introduction of what these inverse semigroups are and this kind of thing. So an inverse semigroup, as probably all of you know, is a semigroup which has this additional property that every element has this partial inverse. To me, every semigroup has a zero. So if you don't have a zero, you need to attach one. So this is a special element which will be preserved by all the maps. So it's this special element. So this is just a usual absorber. And of course, I recall that idempotents in an inverse semigroup are self-adjoint and they commute. So they define abelian semigroup. So in particular, you may view them as meet semilattice with this natural partial order. It also has a zero, so it's a really good semilattice. And a canonical example of an inverse semigroup is this inverse semigroup of partial homeomorphism on a topological space X. So what is that? These are just maps. So there's a partial homeomorphism map defined on an open set D, which maps it onto an open set R, and the collection of those form a natural inverse semigroup with the multiplication, which is just a composition of these maps on the largest domain. So then this is an inverse semigroup. The star is just the inverse of the map. And in this particular example, the idempotents can be identified with the topology of X, because idempotents here will be just identity maps. So if you don't know any of that, so this is like a good picture to think about it. It's like this model example. Every inverse semigroup can be embedded into this inverse semigroup. And in fact, I will mostly focus on ample groupoids. So then it's good to think about is homeomorphism between compact open sets. Okay. So an action on the topological space of an inverse semigroup is just a semigroup homomorphism from S to this inverse semigroup of partial homeomorphisms. To me, I assume that this is a zero preserving map. So here 0 is just an empty map. And one also assumes that the domains of your action cover this whole space X. So it's like this homogeneity assumption. So when S is unital, this just means that this homomorphism H is unital. Okay, so having an action, one can associate the transformation groupoids, and here I mean these transformation groupoids like in the book of Patterson. So very briefly, what are those? So you can look at this product space and use the structure from the action to construct the groupoid there, but this is too big, so you want to quotient out, and then you define this germ relation here, which is nice. I mean, it gives you a nice étale groupoid, but it kind of destroys the topology in the sense that usually those groupoids are non-Hausdorff, they are just locally Hausdorff. But what is nice about this groupoid is that this étale groupoid with the unit space X, and what is also kind of instructive is that every groupoid, every étale groupoid with the unit space X is a transformation groupoid like this. So you just need to take like an inverse semigroup of bisections. We naturally act on the unit space, and the transformation groupoid of this will give you the groupoid back. Okay, so these are kind of standard constructions, so I do not recall them, and I want to construct now a groupoid just out of an inverse semigroup. So I need to find something that my inverse semigroup acts on, and there are plenty of choices. Today I will just focus on two. So first one, this is the first space, is the spectrum of the similarities of idempotents. So this is this nice, totally disconnected space, which can be defined as a set of filters. And this is equipped with the topology where the basic set is the cylinder set. So to any idempotent, I just associate all those filters that contains it. So there are plenty of other descriptions of this space. And so this is one space, and another space that I would like to focus on today is what is called the tight spectrum. So the tight spectrum is this set. So we look at ultra filters, but ultra filters is not enough. So we close it. We close it in this larger space. So close it in this topology described above. So having these two spaces, our inverse semigroup acts naturally on this larger space. And in fact, this smaller space is invariant. So this action restricts to this. So basically, this action is given by conjugation with the inverse semigroup element. And these are like canonical actions that allow us to define the relevant transformation groupoids. So the transformation groupoid for the action of this larger space is what is called a universal groupoid, or some people call it Patterson groupoid because it appeared in the book of Patterson. And the smaller groupoid is called tight groupoid, or one could call it Exel's groupoid because it was kind of introduced and popularized by Excel. So this is a closed subspace of this space, and this implies that this groupoid is a closed subgroupoid of this. But the way I think about it is like that this groupoid is a quotient of this larger groupoid. Okay? So maybe a very quick glance at the kind of most popular inverse semigroup. So this inverse semigroup associated with the most important for sister algebras, the inverse semigroup of a directed graph. So if you have this representation of a directed graph, like in the graph sister algebra or left path algebra, and you look at these partial isometries that generate it, so they also generate an inverse semigroup. So this is what I mean. I mean this inverse semigroup. It can be described abstractly as this fiberwise product. So E star here is just a set of finite paths. So you add 0 to this, and there is natural product that turns this into an inverse semigroup. So for this inverse semigroup, the set of idempotents could be identified with paths, and the spectrum of this inverse semigroup can be identified with just the space of all paths. So this means here that I view that this set consists of finite paths and infinite paths. So this is the path space. And then the tight spectrum is kind of, this is like a motivation for introducing this tight spectrum maybe, is what is known as boundary path space of the graph. So these are just this infinite paths plus this finite paths that start in a singular vertex. So to me, a vertex is singular if it is a source or infinite receiver, because I kind of use this, say, modern nomenclature here. So this is the boundary space. The boundary path space is the tight spectrum here. So we also know that the transformation groupoids here are just nothing but the Renault and the Connu groupoids. So we have this shift map here on this space of paths. And so we know that these groupoids are really nice. So these are like Hausdorff groupoids, they are amenable. And we also know a lot about structure of these groupoids because we know properties of these groupoids, how to describe them in terms of graphs. So in particular, this is, for instance, minimal. This groupoid is minimal if and only if there are no hereditary and saturated subsets in our graph, which is also equivalent to saying that this is a cofinal graph. The topological freeness of this graph is equivalent to saying that every cycle in this graph, so topological freeness of the groupoid is equivalent to saying that every cycle in the graph has an entrance, and etc. So slightly less is kind of known about this groupoid. For instance, does anyone in the audience knows when this groupoid is topologically free?
I should know, but I don't recall.
It is always topologically free. That's, yeah. Okay, so this is like a nice example, and I will destroy it by introducing this self-similar action, but let me proceed. So in general, we know a lot about this construct, these two groupoids in terms of general inverse semigroups. So this is like a combination of several results, but the main contribution is due to Axel and Enrique. So we know now at the moment how to characterize in terms of the inverse semigroup the following properties. So we know how to characterize when the universal groupoid is Hausdorff. This was done by Steinberg and used by him in several papers. We know how to characterize when the small groupoid is Hausdorff, and when it is minimal. We also know how to characterize when it is topologically free, and we also know how to phrase in terms of an inverse semigroup when this group is locally contracting. So combining these properties of the inverse semigroup, we can say some things about the structure of the associated system algebras. In particular, I don't know much more about this universal groupoid, but yeah. Okay, so for instance, I don't know how to characterize topological freeness of this larger guy in terms of the inverse semigroup. So this means that we have this general machinery. Okay, so it is nice, but we want to twist it. So we need to introduce twists. So the cohomology theory for inverse semigroups was developed, but apparently it was not kind of adapted, or it was not used to construct system algebras and study their structure. So that is why we needed to develop this. So very briefly, what is a twist of an inverse semigroup? So for me, this is how we define it. It could be defined in a number of equivalent ways. It's just a collection so to each pair of elements in my inverse semigroup whose product is non-zero. So I view these elements whose product is zero as kind of, as that product is not defined. So I kind of view my inverse semigroup as a kind of semigroupoid. So I attach these numbers only to those elements, and these are the numbers in the unit circle. And of course, I want the traditional cocycle identity. So this is this two cocycle identity, but I only require it when the elements compose. So when the product of these three guys is non-zero, and a normalizing condition, the usual one for any idempotent, I assume this. So this exhausts like the second cohomology class of this inverse semigroup with values in the circle T. Okay, so I will move on immediately to define algebras by representations. So we define the representation of a twisted inverse semigroup on a Hilbert space as follows. So this consists of a zero preserving map into contractive operators on this Hilbert space, such that the obvious thing happens. So this is the product of Vs times Vt is the V of the is T, but twisted by the twist. Okay, and I assume this holds whenever the product is defined. I mean, whenever the product is non-zero. If the product is zero, then I do care. Then it should be zero preserving. So it is zero when the product is zero. So the way I wrote it here using this contractive operators is because this definition generalizes to LP context. If you want, I can say a few words about that. So if you replace your Hilbert space by any LP space, this definition is better because it does not use the word partial isometry. But in the Hilbert space case, in this definition, all these guys will be partial isometries. So because they are contractive and they will have this partial inverse, so I could simplify this definition for Hilbert spaces.
So
the way I wrote it, yes.
In the LP case, do you want the VSs to be spatial in the Phillips sense?
Okay, so if H is an LP space, then I take this as my definition, but I add one more thing. So I add one more thing, that this V restricted to idempotents takes values in Hermitian projections, because it will take values in projections. I assume Hermitian, and then it implies that for LP, when P is different than 2, these will be spatial. So this is our definition. So our definition adds one more condition, that V restricted to idempotents takes values in Hermitian projections. So in the Hilbert space case, this is automatic. And for P different than 2, this will give you exactly that this will be equivalent to saying that these are spatial partial isometries, when the measure is localizable, so when you can make sense of it. So, does that make sense?
Yeah.
Okay. So I want to define also a subclass of representation. So we say that the representation is covariant. So I want to add this covariance condition or Kunz relation or whatever you call it. So in this general picture, it looks like follows. So I want this map V, when restricted to idempotents, to be a tight map. Tight map means that it maps covers to joins, which explicitly means what is written here. So that this product is 0 means that the cover is mapped to a join. And the cover of an idempotent is this kind of semigroup way of phrasing. I view it like this. So there's like a semigroup description of when a compact open set is a union of some compact open subsets. So this is a finite set like this, such that for any non-zero idempotent below E, there is an element in F which intersects this element Z. So for any such finite F, I want to have this.
Yes. So sorry. So yes. The universal sister algebra for these representations will be the associated to the tight semigroup.
Yes.
The right groupoid and not the other one.
Yes. Exactly. This is the reason why we kind of introduce it. So, for instance, just one more sentence. So if we can make this cover to consist of orthogonal elements, so it's like disjoint elements, then this condition could be written. I mean, I could simplify this condition and say just that VE is equal to the union to the sum of the F's for F over all elements in the F. Okay.
If and it's exactly orthogonal, right?
Yes. So when F is orthogonal, I could simplify this, but in general, this is what I kind of have to write, or I can phrase it using the language of tight maps, but I have not introduced it. Okay, so then this is a kind of definition proposition. Then there exists this universal sister algebras, the Toeplitz algebra, which is universal for representations, and this kind of, Kunz-Krieger algebra, which is universal for covariant representations. Okay, so I have defined the universal algebras nicely, but now I want to have groupoid models like Willie said. So I have them without a twist, but now I need to add a twist. So now the question is how to associate a twisted groupoid to such a pair. And this apparently was not done. So this is maybe not very hard, but it is also not very trivial. So this is a bit tricky. So whenever I have an action of my inverse semigroup, any action on some topological space, then the twist of my inverse semigroup induces a twist of this action. But it is like locally constant twist. And we are struggling because it was kind of obvious to us that it should be this natural twist by a cocycle of Sieben, for instance, but it turns out that this is this much more complicated twist of Bose-Exel, this more general twist is needed here. So even showing this was not completely trivial. So we used some relations proved by Ben Steinberg. And it follows from this Bose-Exel paper that whenever you have this twist inversions, this induces the Kumjian twists on the transformation groupoid. But this is actually this really Kumjian twist. So it's like not that in general we can make it a cocycle on the groupoid. It's usually, in general, it will be this topological non-trivial twist. So here I view twists as third-line bundles because I like them. But of course, you may think of them as in terms of these central extensions. But they are not, in general, they are not cocycles in groupoid. This more general structures needed. So I can apply this proposition to the action on the spectrum and the tight spectrum, and then I get the universal twisted groupoid and this tight groupoid, which is twisted. So here I use the same letter because this third line bundle is just a restriction of this third line bundle to this groupoid. So I use the same letter because to me this is like they're very consistent. So these are these twisted ample groupoids that I associate to my twisted inverse semigroup, and then we can prove that we have this isometric isomorphism because this is done for this isomorphism to hold that these algebras that I have defined, they have this corresponding groupoid mode. So this is, I guess, what Willie said was this.
Yeah,
this is that groupoid.
One question. So first an assertion and then the question. When I wrote this paper, I didn't know that there was a cohomology theory of semigroups, and so I wrote the conditions that it looked like it were. And then I learned afterwards that when people talk about groupoid twists, they do not always have a cocycle. They do have it local. So are the groupoid twists that you get from a semigroup twist, do they have a cocycle, or are just this kind of
so this is what I kind of try to emphasize on this level, but in general you will get this just local cocycles, so they are not global cocycles. But maybe I should explain it here because these are ample groupoids. And it is well known fact that when you have an ample Hausdorff groupoid like sigma compact groupoid, then you can trivialize this twist always. So you cannot do it in a canonical way, but you can prove and you can always make this twist to come from a cocycle.
Okay, but in this particular case,
when my groupoids are Hausdorff and sigma compact, then by some abstract I know that this happens. But when they are non-Hausdorff, there are really nice examples. I think I saw them first in the paper of Axel, Pinedo, and Dokuchayev, I think. So very simple non-Hausdorff groupoids, you can make this twist, which is which is topologically non-trivial. So in ample case, this twist will be in general like just only local cocycles. So the punchline is that I cannot turn them into cocycles even in the ample case here because they are in general non-Hausdorff, and this destroys things.
Okay, so L sub omega is not the name of a two cocycle.
Yes, exactly. So I view them as Feldline bundles, but you may view them as these central extensions, and they will be in general topologically non-trivial. So. Okay, so having this proposition, having these groupoid models, now I kind of know how to define reduced objects because I have a regular representation of my groupoids. So I can use this groupoid representation, and I have a regular representation of this groupoid. So I have two natural groupations. I'm not giving you formulas, but they are in the paper. And so I can define natural representation and natural covariant representation, which allows me to define the reduced twisted inverse semigroup and the reduced, so the Toeplitz version reduced and the Kunst-Krieger reduced version. Okay. But since we talk about non-Hausdorff groupoids, this is not the end of the story. So I need to introduce also essential ones. And in order to do it like in a nice way, I will use the following lemma, which you can find in our previous paper with Bartosz and McKee. We noticed that this groupoid G always decomposes into these two disjoint group subgroupoids. So this GH and the remainder, where GH it consists of the set of Hausdorff points in G. So this is what we learned from the referee. So already these are considered this kind of Hausdorff points. So these are these points that can be separated by open sets from any other set in the groupoid. So it turns out that this GH, is a subgroupoid. I kind of disregard topology, but this is a subgroupoid. And what is important is that the remainder is meager. I mean, it's usually meager. So for instance, when you can cover your groupoid with a countable number of bisections and things like that, or if this is a topological principle, I mean, you need to try hard to make it not meager. So in general, I will kind of assume that this is meager just for simplicity. And then we can use this to define essential algebras by concrete representation. So what I do, I restrict my regular representation, this tilde representation, to this subspace because this is the subgroupoid of this. So this is like an ideal. So this representation restricts to this representation of this on the smaller subspace. And I do the same with this representation lambda. So I restrict it to this subspace. And then I can use these concrete representations to define my essential algebras. Okay? All these contractions, because they are kind of spatial, they pass. So you need to prove it in LP operator algebras like this. But this is also not kind of much harder than for sister algebras. And here to define this in LP context, you just need to change 2 to P, and then you get the definitions for LP operator algebras. So in the end, what we get, like in this general picture, we have this algebras associated to our twisted inverse semigroup. They also contain this diagonal commutative sister algebras. So all these contain these algebras of functions on the spectrum of the semigroup of idempotents, and they contain this. So all these algebras have different nice properties that other don't have. But for instance, when it comes to ideal structure, you want to investigate this kind of thing. So by combining the results that I already told you, we can characterize in terms of S, for instance, when this is a Cartan inclusion, or we have nice criteria to in terms of inverse semigroup, showing that this guy is simple or purely infinite and all these things. And so in general, we were trying to understand what is the relationship between these algebras. Of course, in order to understand when these two coincide, you need to kind of go to groupoid level. So this is like a kind of nuclearity assumption when these two coincide. And here we know when these two coincide in terms of S because we know how to describe Hausdorffness of the groupoid. But it might be that these two guys are equal to each other, even in a non-Hausdorff case, when these singular ideals vanish. So this is also some interesting issue, which was also discussed during this seminar. Okay, but this is like a general picture of inverse semigroup, and I want to move to subsimilar actions. Okay, so this is like a second part now. I don't know what time is because I don't have a clock, so please stop me whenever you want to. So we'll start with a small category with objects 0. So I will have like 2 different examples of the small category in mind now. So one example is just a groupoid. So the groupoid is, of course, a small category of all invertible arrows. And if in addition, I assume that my set of objects is a singleton, then I'll get a group. So in other words, a group is a small category of all morphs is invertible and a single object. This is somehow people define this. Okay, and on the other extreme, I have like another example of a small category in mind, which is kind of on the other extreme. So this is the category of paths in the graph. So when I have a graph and I have the set of finite paths, I can turn it into a category. So I can define the composition as concatenation, and it is defined whenever the range and the source of the path agree. So this is on the other extreme, because here all morphisms are invertible, and here like no morphisms are invertible. I mean, identities are invertible, and here I view vertices as identities of this path category. So these are the only morphisms that are invertible. So in this sense, these categories are very different. And so what is a graph with a single vertex? So a graph with a single vertex could be identified with a set, because then this, what you just need to define is the set of edges. But then the path category would be what people call rooted tree. So this is how it simplifies in this case of a single object. And the rooted tree is usually visualized in this way. So this is a rooted tree for the set X with 2 elements. So last week you could see it in the talk of Ali Miller, the kind of the same rooted tree. And the nice thing about these trees is that you can view, I mean, of course, you can study the group of automorphisms of this tree. And of course, the group of automorphisms acts on the tree. But what is nice about this tree is also that the tree gives back. So also the tree acts on this group of automorphisms. So if you fix your favorite automorphism of this tree and fix a branch of this tree, suppose this is a branch, then this branch kind of gives us this part of the tree which is isomorphic to the whole tree. So I can view this as a whole tree, and the fixed group element of this isomorphism of this tree will map this piece into another piece which is looks the same exactly like the whole tree. So in this way I will get different isomorphism of a tree. So combining this isomorphism of the tree with this branch, I get another different isomorphism of the tree. So this tree acts in this way on the group of automorphisms of the tree. So this is this self-similarity. So we have action on the tree, and tree acts on the group that acts on the tree on this level. So this kind of looks weird and complicated, but from a distance it looks really nice. So I can phrase it in terms of this matched pair of categories. So this was done by Alex and Aidan. So we consider this very general framework of two small categories which are matched in this sense that one category acts on the other acts on the first one, and they are combined by this one cocycle identity. So one action is one cocycle for the other, and the other is one cocycle for the first one. So the picture is very, very symmetric, very general, and very, very symmetric. And from this picture, you can see actually what is going on. So when you apply this picture to these categories here, you will exactly get what is called as the general self-similar groupoid action. So this is exactly an action of a groupoid on the path category. The path category acts on the G in this kind of symmetric way. The asymmetry comes from the fact that the categories are kind of on two different extremes. And here, the one more point that one should add to characterize fully this self-similar groupoid action as its matched pairs is that the left action preserves lengths of paths. So it's like an additional piece of the structure. Okay, so when we apply this to this case when there is only one object, we get what is called a self-similar group action on this rooted tree. And here one usually assumes that the action of the group is faithful, and then the group is called self-similar group. So this all stems from that. You know all things about it because you've heard a number of talks. An important fact is that Nekrashevich associated sister algebras to these guys here. And it was very nice, but I think it really took off when Enrique came with Rui, and they generalized this to these group actions on finite graphs. And here now we want to study these things in the full generality. We have lots of other pictures. So one nice picture is also that these self-similar groupoid actions, the special matched pairs, are equivalent to what is called a groupoid correspondence. So groupoid correspondences are like sister correspondences, but you replace sister algebras with groupoids. And when you assume that your groupoids there are discrete, then it's exactly equivalent to a self-similar groupoid action. So this is kind of another picture, equivalent picture, which is really nice. So this was noted by Antunes Kohlmeier, and it's very useful in this analysis. So in particular, Ali Miller and Steinberg, in the paper that Ali discussed last week, they use this approach a lot. And this is really nice approach when you want to study homology, key theory, and all these things. There's also a different picture when you can view this self-similar groupoid action as a groupoid acting on trees of the forest generated by the graph. This is also very nice. There are also, you can also associate, because this is a matched pair, so you can also do these two people. So who knows, who are they? So you can do Zappa and Shep. So from these two categories, you can produce one category, and this approach was taken by Ortega Enrique, by Edward Enrique. So you have all these plenty nice pictures, approaches that you may choose and start with. We give a brief survey in our paper, so if you don't know much about it, you can look there. There's also a nice survey by Enrique, now lots of sources about that. So we decided to work with the definition which contains the smallest amount of data. So here's our definition. So we wanted to define with the smallest number of things needed to this. So for us, our definition, the self-similar action of a groupoid on a directed graph. Here we assume that the space of objects of the groupoid and the set of vertices they're the same set. So this is the left action of the groupoid on the set of edges, together with a kind of nucleus of this left action of the path space on the groupoid. So we just here act with edges on the groupoid, which satisfy this one cocycle identity. So this is basically what we start with. Of course, we need to add some more conditions to make this sense, but these are just technical blah. So the crucial thing is that starting with this, we can extend the structure uniquely to this pair, to this matched pair of categories. So we can extend this left action to the left action of the groupoid on the path space. And the path space, this action of the edges on the groupoid extends to the action of paths on the groupoid. So that situation is kind of symmetric. I mean, it is symmetric, but the categories are different. So this is what makes you kind of dizzy. Okay. So this is our definition, and now we need to define a twist. So here's the definition of a twist of a self-similar action. So this is kind of our new input. So this is a pair of maps. So first one is just the usual groupoid cocycle. So this G is just a discrete groupoid. So this is just a groupoid cocycle. And this sigma bow tie is, I don't know, like a linking map. This is what I would say. So this is a map on this fiber-wise product, which satisfy this strange formula. And here we should enter. Here he is. So as far as I know, you consider the case when this is trivial. So you kind of disregard this groupoid cocycle. So when this vanishes and this vanishes, then this formula is just what you have in your paper. So this is the one cocycle, another one cocycle. I don't know for what. Right? Okay. And you also consider a completely different, I mean, maybe not completely, but you consider this algebraic picture. So but the reason is that why we define it like this. So of course, when you twist the graph, it can always untwist it because like Z graded, so the cohomology is trivial. So that is why there is no twist on the graph. But the punchline is that with this definition of twist and the theory of these guys, we can show that this exhausts the second cohomology class. With this definition, we exhaust the second cohomology class for this matched pair here, or equivalent to the Zappa-Szep product. So these are like general twists for this structure. This is what I'm trying to say. Okay, so quickly go to algebras defined by representation. So we define a representation of such a pair or of such a triple or such a pair which is sigma twisted. So this is a pair of maps. So one map is on the groupoid, the other map is on the set of edges, such that the representation groupoid is the usual sigma twisted representation of the groupoid, and the map T is such that this set of projections corresponding to vertices and this set of edges, the operator corresponding to edges, is an E family. So this means that the range projection to this partial isometry is just this operator corresponding to source, and the range projection is not greater than the projection corresponding to the range of G. Okay, and we need one more relation which kind of combines the two maps, and here is where the sigma bow ties enter. So we have this computational relation that WG commutes with tau E in this sense that if we want to move this VG to the right hand of tau E, but we need to add this bow tie here, and GE acts on E, and then the moved V is not G but G section with E because G was already acted, so we remember this action. And this is all that you need kind of to define these general representations, but of course we want this kind of covariant representations or Kunz-Krieger covariant representations. So then we add one more relation. So this is this relation. Maybe this is not one relation because it corresponds to every single regular vertex. And maybe a slightly novelty, we also introduce this Coburn-Toeplitz covariance, which is kind of opposite to Kunz-Krieger. So we don't have this equality for any vertex V. And then with these definitions, you can quickly define system algebra. So you can define the universal system algebra of this all representations. This is the Toeplitz algebra. And then by concrete representation, we can define the reduced one and essential one. So all these contain a number of interesting system subalgebras. So for instance, all of them contain the Toeplitz extension of the graph system algebra, which means in particular that they contain this diagonal algebra of these functions on the path space. And what is also nice is that this Toeplitz algebra contains the groupoid system algebra of this twisted groupoid here. The reduced one will contain just some exotic completion, I don't know which one. And the essential will also contain exotic, provided that the graph is row finite. In the non-row finite case, this could be non-exotic. So this could be something below reduced. So this is something interesting. And of course, using Kunz-Krieger covariance representations, we can define the corresponding Kunz-Krieger system algebra. So this is a universal system algebra for Kunz-Krieger representations. This is a very reduced version. So all of these are generated by Kunz-Krieger sigma representations of our structure. And they also contain the graph system algebra, so they contain the nice diagonal system algebra. And on the level of the groupoid, they contain just something. So it's just some house of completion. It is not clear what is that in general. So I should also mention that these all algebras are defined by sigma representations, but in fact they are Coburn-Toeplitz representations here with these guys. Okay. So I don't know how much time I have. Probably I don't have any. So move on.
5 minutes is fine.
Okay, so move on to results. So we have defined this similar groupoid action. So we defined these Toeplitz algebras, we defined Kunz-Krieger algebras, and so we can also associate this twisted structure. We can associate a twisted inverse semigroup. So the recipe for this is that the semigroup is like given by these triples that you can associate to these operators, and looking at the relations that I presented on the previous slide, you can kind of guess what the semigroup is. And in fact, you can recover also the twist of this inverse semigroup. So typical formulas will look like this. So having this twisted inverse semigroup, we can associate to them this twisted tau groupoids, this universal and a tight one. So we have nice groupoid models for our sister algebras. And also we can associate to the sister correspondence, which looks like something like this. So it's like a tensor product of the sister correspondence of the graph tensor with some completion of this algebra. And in this way, we get a Toeplitz-Pimsner picture of this Toeplitz algebra by the sister correspondences and relative Kunz-Pimsner for these algebras. Okay, and now combining these and reading of the properties of the inverse semigroup and the graph, the groupoid, we have the following conditions that appear naturally. So we have this condition that every G cycle has an entrance. This corresponds to topological freeness of this graph, groupoids, sorry. But in fact, we need one more condition in general, which does not appear in the literature. So this is what I call average. So this is a condition that says that every path in here, if you have a G that fixes every path, then it has to strongly fix some paths. Strongly means that the G acts on the path, it fixes the path, and when it's acts on the path, it becomes a unit. So then it fixes all the paths. So this is this strongly fixing. And this condition was not visible in previous works because when you consider faithful actions or finite graphs, this is automatic, so you don't have to consider this. So these two conditions are equivalent to topological freeness of this groupoid. This condition, together with Av, is equivalent to topological freeness of this universal groupoid. This condition that every G admits finitely many minimal strong G fixed paths. So this is a standard condition in this business that is equivalent to Hausdorffness of the smaller guy. And here it turns out that the Hausdorffness of the smaller guy is equivalent to the Hausdorffness of the larger guy, which in general is not true. And mean, it stands for minimality. So graph, this inverse semigroup of graph is minimal if there are no hereditary saturated subset of the vertex set, and here we just add just G invariance. So this is very natural motion. And we also have this corresponding notion to this contractivity. So combining this, here are some results, a brief sample. So we have this uniqueness property. So if you combine these two conditions, then for every Kunz-Krieger representation, non-zero Kunz-Krieger representation will give you something that lies between the universal Kunz-Krieger algebra and the essential algebra. So if these two coincide, then you have like honest uniqueness theorem. If you have these two conditions, in fact, this is like if and only if. So if you have these two conditions are equivalent to saying that for any Coburn Toeplitz representation, non-zero complex, this one has to be non-zero, you also have the same thing. So it's like this general uniqueness property from graph system algebra theory. And we can characterize when you have Cartan inclusions. So these three conditions are equivalent to that this canonical diagonal is a Cartan inclusion, the reduced Kunz-Krieger algebra associated with these things. These three are equivalent to having this as a Cartan inclusion. This correspondence picture allows us to talk about amenability and nuclearity. So if group G is amenable, then all algebras are nuclear here. So in particular, these Toeplitz algebras are nuclear. So in particular, the universal and the reduced one coincide. The same on this level, on this Kunz-Krieger level. And here a funny thing is that for row finite graphs, this nuclearity here implies actually that the universal coincides with the essential one, so that the essential ideal disappears here. Even though the groupoids might be highly non-Hausdorff, somehow on this universal level, this destroys this singular ideal here. And the last result, to summarize, simple, purely infinite system algebras. So if we have these two conditions plus minimality, then they give simple system algebra. So then this is simple. And if we add this one more for this contracting, local contracting property, then our essential algebra is simple, purely infinite. So thank you. And I'm sorry, so sorry that I kind of probably went over time. Like,
No.
Thank you.
It was fine, and it was very nice talk. Yeah. So I have a. So have you looked at the effect of the twisting in Kasparov's KK? Say when the group is the integers.
No. So we did not study at all this. Homology, K-theory, nothing like that. I mean, so of course, I mean, the paper of Ali Miller and Steinberg came out like in the meantime. So we did like a lot of homology K-theory. We did not touch that. So we kind of were focusing on the ideal structure. We did a lot of computing with this inverse semigroup. So we played a lot with this. So I found it interesting to understand what is going on this inverse semigroup level. But no, we did not even attack this kind of question. So the paper is already too long.
Okay. Enrique raised his hand. You have a question, Enrique?
No, it was a mistake. Sorry.
Okay, sorry. This I asked this KK question because my motivation for introducing these twists was that when you take the presentation of the Katsura algebra as a quotient of the so the Katsura algebra is the algebra of some tight groupoid, which is a quotient of a corresponding Toeplitz algebra, say, and then you show and the ideal is an ultra-material thing, and then so you have a sum of copies of the group algebra of the integers for both the ideal and the Toeplitz one, and well, the algebra of the integers is a copy of the ground ring plus a suspension, right? So just as the continuous functions on S1 are the suspension of the complex numbers plus the complex numbers. So the maps that you can have are matrices that involve maps from the complex numbers, say, to itself. So that's an integer, it's a K0 element. Then maps from the complex numbers to the suspension, but that's K0 of the suspension, which is 0. And then maps from the suspension to C, which is K1, which in the sister case is 0. And then from the suspension to the suspension. Right? Now, which is again a K0 element, so it's an integer. And so in the purely Katsura case, I didn't get any K1 element. So any map from the suspension to the complex numbers. And in the sister case, this doesn't matter because K1 of the complex numbers is 0, right? The topological one. But the algebraic one is. And the way to produce a map there was to introduce the cocycle. So the cocycle produced this map. So I wonder, I mean, I would suspect that in the sister algebraic setting, this will make no difference because whatever cocycle you would put will give a 0 element in K1 because K1 is 0. So if your algebra is, say, a Katsura, it's purely simple, purely infinite, then it is characterized by this K theory, and so it should be one of the others. Which, by the way, every Kirchberg algebra is a Katsura algebra. So, yeah, but so that's so this long description is because, in general, I mean, there might be some interest, say, in the presence of a classification theorem, that you want to say that when you twist, you get something new that it wasn't there before, right? A way of saying this is that the invariants are different. The K theory is different, or the basis or whatever. Yeah, okay. Sorry. That's my motivation for the.
Yeah, I understand that your motivation was different. I mean, my motivation was that I wanted to understand these things, and I wanted to have a general twist, right? And so, but I have kind of, so as far as I know, it's like not kind of decided whether we actually need twists for the classifications. Am I right? And another remark is that here we deal with these non-Hausdorff groupoids, right? So formally, we need to know that they satisfy UCT.
Yeah.
For instance, because I could not be present last week, but I watched talk of Ali, and he said that oh, he has this groupoid model, and so this is classifiable, so he knows what is that. But do we really know? I mean, can we like really apply classification theory when we know that we have just non-Hausdorff groupoid? Do we? I mean,
I don't know about the full Elliott invariant, but okay, theoretically, if your algebra, if you can show a finite presentation, so that say the Toeplitz algebra is equivalent to sums of copies of the complex numbers and its suspension, and the same with the kernel, then your algebra is in the bootstrap class, and so it satisfies UCT.
Yeah, true.
So,
also,
but
I could use this kind of Toeplitz Pilsner to prove to get UCT. But for instance, here when we have a relative Pilsner picture, then I don't know, and then I cannot even use this. Yeah, so you need to use some other methods. Maybe in some particular examples you can argue like you said, right? But it would be good to have like a general theorem that even for non-Hausdorff groupoids, you always have the UCT. So that would be a good thing to have. But we still don't have, right?
Yeah, no, certainly not. Okay, so are there any further questions from the audience? Otherwise, I shall stop the recording here.